In the last video, we understood why benzene prefers substitution rather than addition. Now it's time to understand that concept in action through one of the most important reaction of benzene, that is nitration of benzene. Let's break it down step by step. Hi, I am Dr. N. Swathi. In this video, we will explore the nitration of benzene, a classic electrophilic substitution reaction that introduces nitro group onto the aromatic ring system. So the nitration of benzene involves three steps. The first step is formation of electrophile. So in this particular reaction, nitronium ion will be generated as electrophile. And in the next step, the formed electrophile will be reacting with benzene to form resonance stabilized carbocation. And later in the third step, deprotonation of this carbocation occurs to form nitrobenzene. Now let us consider this step by step. In the first step, nitronium ion is generated by the reaction between concentrated sulfuric acid and concentrated nitric acid. Concentrated sulfuric acid is considered to be stronger acid when compared with nitric acid. It is because of this reason, nitric acid causes abstraction of proton from sulfuric acid. That means out of two protons present in sulfuric acid, one of the proton is abstracted by concentrated nitric acid. And that is how nitric acid will be converted to give protonated nitric acid. After losing this proton, sulfuric acid generates bisulfate ions. The protonated nitric acid in the later stage undergo dehydration and it generates nitronium ion, that is the electrophile in this particular reaction. Here, the bonded pair of electrons which are present between oxygen and nitrogen are completely transferred onto the oxygen to remove the positive charge from oxygen. And that is how dehydration occurs. And as these bonded pair of electrons are transferred to oxygen, now the nitrogen becomes electron deficient. And that is how the nitrogen gets positive charge and thus results in the formation of nitronium ion. So once electrophile is generated, the next step is attack of electrophile onto the aromatic ring system. So here the generated nitronium ion acts as electrophile and it attacks on the benzene ring system. Because nitronium ion is an electrophile, it utilizes one of the pi bond electrons of benzene to make a bond with the ring carbon atoms. And that is how nitro group is attached at the first position on the benzene ring system. Let us number this particular benzene ring for convenience purpose. Let us say now the nitro group is attacking on the first carbon atom utilizing the doubly bonded electrons present at first position. In that case, the second carbon, it becomes electron deficient and that is how a positive charge will be generated on the second carbon. So on attack of nitronium ion onto the benzene ring system, it results in the formation of carbocation. Now this carbocation has several resonance structures. So how we can get those resonance structures? Let us see. Now in this structure, positive charge is present at second position. Now at third position, there is a double bond. So if you shift the doubly bonded electrons present at third position to the second position, then a new double bond will be obtained between 2 and 3 carbon atoms. And simultaneously, now the fourth carbon, it becomes electron deficient because the double bond is transferred to 2 and 3 positions. And it is because of that reason, fourth carbon attains positive charge in the newly formed resonance structure. We can draw one more resonance structure for this structure. So that is by transferring the double bond which is present at fifth position to the fourth position. If you shift the double bond present at fifth position to fourth position, then a new double bond will be obtained at fourth position. But at the same time, now at sixth position, there is deficient of electrons due to the migration of the double bond. And that is how this sixth carbon of benzene ring, it attains positive charge. And thus results in the formation of another resonance structures. So these are the three resonance structures possible for the resulting carbocation. This resulting carbocation is also known as benzenonium ion or arenium ion in case of electrophilic substitution reactions of benzene. So the resulting resonance structures are usually shown with double-sided arrows because one is obtained from the other and they will be always shown in brackets. So if you observe these three resulting resonance structures, we can make out two important points. The first carbon atom of this carbocation is tetravalent because it has nitro group on it. And the second important point is the two double bonds as well as positive charge on the ring carbon. These features are migrating between 2 to 6 carbon atoms in all these three resonance structures. By combining all these resonance structures, we can write its corresponding resonance hybrid like this. So we have drawn a cyclohexane ring with a tetravalent carbon at first position where nitro group is present on it. Okay, and delocalization of pi electrons are shown between 2 to 6 carbon atoms. And also you can see in the resonance structures at 2, 4 and 6th position, the positive charge is present. So to represent this delocalization of positive charge over these atoms, we will keep a positive sign in the center of this particular ring system. So this is how the resonance hybrid structure will be represented. In the third step, immediately the resulting carbocation undergoes deprotonation. So here the first resonance structure is considered. It undergoes deprotonation. So for this reaction to facilitate, bisulfate ions which are formed in the first step will be utilized. So these bisulfate ions causes abstraction of proton from the resulting resonance stabilized carbocation. So when these protons are transferred to bisulfate, it results in the formation of sulfuric acid as the byproduct. So the bonded pair of electrons which are present between hydrogen and carbon will be migrated in the form of double bond to compensate the positive charge present at second position. And that is how the third pi bond will be restored in the resulting structure, thus results in the formation of nitrobenzene as the product. So this is how nitration of benzene occurs in 3 steps. The first step is the generation of nitronium ion by the reaction between concentrated sulfuric acid and concentrated nitric acid. And in the second step, the resulting nitronium ion attacks benzene ring and thus results in the formation of resonance stabilized carbocation. And later in the third step, this carbocation undergo deprotonation by the action of bisulfate ions and results in the formation of nitrobenzene as the substituted product. So in this reaction, the second step, that is formation of resonance stabilized carbocation, is the rate determining step because the overall rate of the reaction, that is how fast the nitrobenzene or the substituted product is formed, it depends on how fastly or how easily the carbocation is formed in this particular second step. It is because of this reason the formation of resonance stabilized carbocation step is considered to be rate determining step. So in addition to nitration of benzene, benzene undergo various other electrophilic substitution reactions. A few are given here. So benzene undergoes sulfonation in the presence of concentrated sulfuric acid and it gives benzene sulfuric acid as the product. Upon halogenation, benzene gives halobenzene when it is treated with a combination of chlorine and ferric chloride. It also undergoes Friedel-Crafts alkylation reaction when a mixture containing alkyl halide and aluminum trichloride is treated with benzene. It results in the formation of alkyl benzene. Another reaction, Friedel-Crafts acylation reaction, where a mixture containing acyl chloride and alkyl chloride is allowed to react with benzene, which results in the formation of a ketone. So these are the few more examples for the electrophilic substitution reactions of benzene. If you look at this nitration of benzene step by step, we can make out one thing. In the second step, that is reaction of nitronium ion with benzene ring system, seems to be an addition reaction because the nitronium group gets attached to the benzene ring system on its first position by utilizing the pi pair of the electrons. So it seems to be like an addition reaction. But in the third step, deprotonation occurs and those bonded pair of electrons which are lost in the second step will be restored in the structure of benzene, and that is how the resulting compound preserves its aromaticity and thus it is considered to be stable. So benzene, even though it is resonance stabilized, it reacts, but even after substitution reaction, it preserves its aromaticity. If you found this video useful, then give it a like, subscribe my channel so that you will never miss my next coming videos. Thanks for watching and stay tuned to my next videos.